Today I'm going to be talking about smart services and smart clients, and basically how we use microservices at Runscope and how it's kind of helped us around how we build and deploy code. So some context at Runscope, we build tools that help developers solve API problems. One of those tools we built is Runscope Radar. So it's a way to build tests. Imagine chaining a bunch of HTTP requests together and being able to, let's say, extract some variables, stuff them in, extract some values, stuff them in variables, use them in subsequent requests, write assertions against those to see what's coming back, and basically letting you know that your API is up and running, it's healthy, and it's performing properly. Another tool we built is called Traffic Inspector, and it allows you to debug in-flight HTTP requests. So it gives you a real-time stream of the data that's flowing between the client and any APIs that you use. It includes timing information, status codes, full request and response header and payloads, and so on and so forth. And so those are the tools that we built, and we built them on top of microservices architecture, which is over 60 services that are all independently deployable, but with only a team of 9 people. 9 people as of just like last week. So in the past year, microservices has become quite a crazy buzzword. And let me assure you, we did not just jump on the bandwagon. This is something that over 2.5 years ago when we started, we made a very conscious decision that we wanted to build software a certain way. And that was part of that decision was to build it, to build small services. So why did we make that choice? There's a lot of moving parts. Why introduce that type of complexity, especially when you're just a very small team like we were, or that we are right now? And for us, our answer to that question was the ability to scale the infrastructure. So to be able to handle the growth of the company, to scale with the demand of our service, which is very much up and to the right, and also to scale our team, make sure that our processes and the way we develop software kind of maps to the way we coordinate our teams and how we handle the overhead that comes with that growth. So a lot's been said about microservices. There's a lot of swell talks and articles out there about what they are, how they work, why you should use them, and most recently, like maybe why you should not use them. So in this talk, I'm going to touch on some of those things, but I really want to focus on how we do things in practice at Runscope, the technology we use, how we organize our code and our systems, and basically how we make this whole thing work for us. So from a high level, I talk very fast, by the way, and plus I have a lot of content to cover, so I'm going to go really, really quick. If you have any questions, please ask me after. From a high level, one of the core reasons we chose this architecture is because, by definition, microservices are all highly independent, small components. And for us, that means independent code bases, independent deployability, and independent teams that they can own different parts of the stack without having to, that obligation of having to coordinate between each other. So needless to say, there's a lot of moving parts, and lots of things changing, and a lot of things being shipped to production all the time. And it takes a lot of work to make sure that things run smoothly and just don't crash and burn and don't fall apart. So the biggest lesson that we've learned over the past 2.5 years is of running microservices is that if you don't invest in infrastructure, you should not invest in microservices. So another way of saying that is that microservices architecture is taking a decade-long picture of what traditional service-oriented architecture is and applying a DevOps bent to that. So applying a lot of automation and infrastructure tooling around it is what makes it all possible for us and for most. And to give you a more concrete example, in the beginning we had our dashboard, which is like our website, and it's a service. And we wanted to build another service that would help us encapsulate all of our customer data to kind of give it a data access layer. And we called that service Identity. So it lets us get information about customers, information about their teams, and generally it's a service with a bunch of get input operations on configuration data. One's blowing up over here. Okay, so we have these two services deployed, one on host 001, one on host 002. So you think, how do I actually implement this function, get teams? And so it's pretty straightforward. We're doing this using the requests. So the request is a Python library that's similar to LWP and Perl. And in this code, we're just setting URL to that host 002. We're making a GET request, and we get the response back in JSON. So this is code, and it works, kind of. And I say kind of because the tricky thing here is that when you're kind of doing things hard-coded or in a monolithic pattern, compared to a microservices architecture, things are always changing. So for instance, we spin up posts, and they might crash, they might spin down. we're dynamic, we're scaling, and you have to change or replace hosts. So for instance, what would happen if I needed to change host 002 to host 003? Basically, I'd have to change code, deploy that, and just to address this new location. And a bigger question here is that what happens in multiple environments? So I have my local dev, or my testing, or my production environment, and all those things need to talk to different hosts. So to my local machine, to my testing cluster, my production cluster. And so hard coding these host names can turn into a huge mess, and we wanted to avoid all of that. So the first thing you have to answer when you have all these services like we do is, how in the hell do you find that service? And so our answer to that is something that we built called Smart Client, and it does several things. First, it's a wrapper around the Python request library. So you just kind of drop it in wherever you use requests. It has the same API, responds with the same objects. And the next thing we wanted to do is get rid of those host names. So we invented something called service URLs, which looks like URL, except it's service : / service name. And the really nice thing about it is that whether you're working in your local, your test, staging, or prod, it's same code. You don't have to change code or update it at all just to address different environments. So Smart Client does three main things for us. Again, it's a service discovery layer. It can translate that service URL into a host name at runtime. Next, it'll automatically retry, get put, and delete those idempotent requests. So for instance, if a network service was down, it just couldn't get to it. If it's safe, it'll retry it, and it may succeed on the next try. And lastly, another nice feature is that it gives you the option to run requests in an async manner. So if you had a bunch of requests and you wanted to fire them all at once and then kind of handle them as they come back, you're not blocking or waiting as if you would have to do if you did those in a serial manner. So the next question is, how does it actually work? You know, what's the mechanism behind it that's powering all of this, particularly in this cluster configuration? And for us, the answer is also a service, and it's called Atlas. And Atlas contains information about how our cluster is mapped. So Atlas stores info in DynamoDB and Zookeeper. So whenever a new service is created or it attaches to a new host, we record all those bits of metadata. And so for instance, in Zookeeper, we kind of have this directory structure. It's where it starts off with hosts, service name, the actual host where it is, where it's located, port number, and some other flags like whether it's enabled or disabled. And so Atlas is a service that encapsulates all of our cluster configuration information. The next part of this is a Python daemon that we call Sidecar. And Sidecar runs on every single host in our cluster. So it does a few things. First, it runs a copy of HA proxy locally. So every one of the hosts has its own copy of HA proxy. It gets its config by reading the info from Atlas. And once it does that, it sets up Zookeeper watches on on those keys, whether it's disabled or enabled, or if you've added a new service or a new host. Any changes to that will kick off a reload of HA proxy. So what in fact happens is you've got this cluster, machines with Sidecar and HA proxy running on all of them. And whenever you make a service call, you're actually taking that service call and you're making it to localhost. So a request to service A will get fanned out to find the service where it's located, where it's living at that time. Same thing with B. You make a request to localhost and it fans out. So it makes the implementation of what Smart Client does pretty darn simple because it just takes a service URL, parses out the service name. We use a custom header, that runscope service, and passes that to the service name, passes that service name in there, and the actual request is made to localhost and that front end port at 4000. So an interesting thing we're doing in the HA proxy, if any of you guys use it, is that we're using the ACLs feature where you can dynamically route a request based on information that's coming in the request. And in this case, you see we're binding it to port 4000, HTTP mode, and we're doing an ACL match, basically a pattern match on runscope service header. And if it has API, then it essentially assigns that ACL, and then down below it will instruct HA proxy to use that backend, the API backend. So we have this one stanza for all of our services, and depending on what header is present, it'll choose the appropriate API. I'm sorry, the appropriate backend. So that makes the implementation really easy. So when we originally built Smart Client, we had a lot of these things hard-coded, like the service names and the port numbers, and they were kind of baked into the library. And so whenever we wanted to make a new change or launch a new service, we'd have to update that library, do a build, and then redeploy all the services that affected. So moving to HA proxy with a dynamic header routing, instead of doing a code deploy to pick up a new service, it's all data driven now. Instead of just making changes to code, we can just essentially add or change a record in the database. So for the code now for Smart Client, it's very static. It doesn't change. We don't have to do new builds or deploys every time that we deploy a new service or make changes. So Smart Client was our answer to that first question, how do we find that service? And the next question is, how do we make service building easy? It's supposed to be fast, right? So our answer to that, as you may guess, is another service called Smart Service. And Smart Service is a library that's built on top of Flask, which is a framework, and Flask RESTful, which is an extension to that framework that helps to build REST APIs easily. We started with this base, and we started adding more packages on top of it, kind of bundling together a lot of things, a lot of common features and functionality that we need across our application. And one of those packages is an open source project that we put out there called Health Check, which basically gives like a health check endpoint to Flask apps. Next set of packages were kind of some third-party, a combination of third-party and some internal things we built. Bugsnag is a third-party tool that we use for exception logging. Runscope daemon helps with daemonizing processes and async and creating async tasks. Alchemist is for database connection handling and management. And then there's this thing called Smart Config. Smart Config is kind of something that helps us where we used to kind of have all of our hard-coded constants and API keys stored into some file, and which is great because the way that you refer to them is really simple. That interface is great. We wanted to keep that interface, but we didn't want to have it so that we would actually be baking these secret keys and secrets into a file that that we'd be checking into GitHub. So instead, it can get those values from Atlas. So you can provide empty placeholders, and it'll query Atlas, pull down those variables, and replace them so that we don't have to be checking in code with secrets. So here we're initializing a Smart Service with a config, and basically what you get is an app object, and it's basically a wrapped Flask app. So it has all the normal things that a Flask app has. So based on the values of the config, we can get, we can inherit a lot of things. So just from like import current app, I could say current app.realm to find out if I'm in test or prod or my local host. Or if my config had like Redis configured, I automatically get a Redis client connection. I don't have to think about like, hey, where is that Redis service? Which one do I use? Connection pooling. You don't have to think about any of that stuff. You just kind of think, okay, I'm going to import this app. I'm going to get this Redis client and start using it. Right? And then same thing if it was Postgres or whatever. So one of the things Smart Service does, it kind of builds a common logging configuration. So everything's standardized. We format all of our logs. We configure our log formats all in one place. So as a developer, you don't have to think about, how do I access a logger? How do I choose the right one for access or error log? So for instance, if I wanted to use Bugsnag, I just import that and I use it. This is one good example of how we build consistency across all of our different services. So another feature of Smart Services on the whole easy part that I was talking about, that these things should be easy, is that we auto-generate these service skeletons. So since all of our projects kind of look, behave, and act the same way, we have one command, generate service. And it does a lot of the early heavy lifting for you. So it constructs a new service object, sets defaults, gives you a Git repository, installs a virtual environment. So you run one command, you get a fully operational service that you can deploy right away. And it gets that overhead out of the way that, perhaps it can help you move on to actually writing useful code and not worrying about the stuff going on behind the scenes. So the Smart Service and all the things that we put into it, as well as Smart Client, they go into this idea of reducing cognitive overhead. The amount of things you have to think about, the amount of times that you have to context switch, it's significantly reduced. So thinking about the database and where is it located and how do I construct a new SQL alchemy model, how do I find a database session, do I need to tear that thing down? You just have to think, like those things are handled for you. You just have to say, hey database, do this thing that I want, and then you just move on to the next thing. So this is really helpful for managing lots of services because all these services, again, they behave and they act the same way. You don't have to focus on the minutia. You just focus on writing code that moves things forward. So that's what we did to make building services very easy. And we have a lot of services. So the next question is, so what happens when you have so many services? And the answer is there's a lot of things happening. So I'm going to talk about some of the lessons that we've learned and the things that we've decided to kind of bake into our processes that makes living with a ton of services really easy from day to day. So the first lesson we learned is they have to automate everything. So for us, that means setting up new servers and bringing them online. We use Puppet to generate templates for init scripts and our monitoring. Everything that we do has to be repeatable and deployable without having to really think about it. So you have to invest a lot in DevOps, invest in automation tools and building scripts that makes it reasonable to manage so many services. The next thing we learned is that through building a nice set of tools like this is that you kind of become language agnostic. So most of our stuff's in Python, but as I said earlier, that about a year ago we started writing a lot of Go code. So once you have the Go service up and running, once we had it running, it became really easy to integrate with the rest of our cluster. So you get a lot of nice services that all the services that are already there, you get to inherit those. Go doesn't need to know about, what format the data's in or the database ORM. It just needs to know that it has an API, this is how you access it, and I can get all this data back in JSON. So we were able to quickly spin up projects and third-party tools, basically anything that talks in HTTP. HTTP was immediately useful to us. And so we kind of say that HTTP is our common language. The next bit, though, was more of a philosophical decision for us early on, but it's really paid off. And that is, there are no shared databases between our services. So imagine a world where you have a dashboard, our traffic gateway, and our API, and they're all talking to the same Postgres database for customer data, like for the identities. The problem you encounter with this type of architecture is that you have the shared dependency, and not only the type of database, but the schema itself. So if you need to modify the schema at all, add a column, or make any changes, you're going to have to update and or deploy code to all these services that depend on it. And the real problem is that you no longer have this independent system. In fact, you're taking away what used to be 3 independent services, and you're really tying them really close together like this, right? So whenever you have a pattern where when you make one change, but it affects the entire system, you have to redeploy in all these other areas, you know you're doing something wrong. So for us, we said, nope, we're not going to do that. We're not going to have this one central data store. So every service owns its own data store. So for identity, it has Flask, Postgres, and its own Redis instance. And the thing is that from everyone else's perspective, it's just an API. You don't need to know what technologies are beneath the hood unless you're actually the one that's developing that service. So if you're developing something for the website or you're adding a new feature, those tech details are completely irrelevant to you, right, in your day-to-day work. It helps keep that mental overhead small, and it makes it easy to change things independent from everyone else around you and the things that they're working on. So the biggest effect of adopting this architecture is that it makes deploying really, really easy. So it's something we wanted from the beginning was this idea of a one-click deploy. And so not surprisingly, we built another service called Prometheus, and this helps us with our deploys. It's like an operational service dashboard. You can see in the middle here, you see all the branches for this particular service, and you can deploy it to test or prod any realm that you want. You can change the realm in the top right hand there. And then there's a snapshot. We use Jenkins for our builds. You can see whether the last build passed or failed for our unit tests. And the idea here is we want to make it simple to get a service deployed to our testing and prod environments that on your very first day of working in RunScope, you can check in code and just deploy it, and deploy it to production as an engineer. And since all of our services are running independent from one another, we have a rule that once your code's reviewed and it's merged into master, that you're responsible. You're the one that can immediately go and deploy it yourself. So we found that people really like doing that. So right now we're close to, that's back in March, but now we're closer to 100 deploys a day, even though we have a very tiny team. And so the next question is, when you're deploying code so quickly, how do you not break things all the time, right? So for us, it goes back to our product. We actually use our own testing tool to monitor our own internal services. That's a huge lifesaver for us. We create service tests through RunScope Radar. After you deploy, it automatically triggers a test, and it verifies all the services are running right, and it's returning the right data. And if things go south, we get notified by email or Slack, or any other integration if we wanted to use like PagerDuty, for instance. So the nice thing about the tool is that we can write one test and use variables in the host name, and we can reuse it over and over again. So if I'm testing on my local dev, or if I'm testing on the testing environment, deploying to test, we can automatically trigger tests to run, or even in prod, I can reuse that same test and do it on an automated schedule so that we know that it's up and running and performing very well over time. So the idea here is that all these things together, smart service, smart client, and our own testing tools, they make this graph possible. So an engineer can spend less time responding to a ticket, and in fact can probably solve the bug faster and deploy it to prod then it do that in a shorter amount of time than it does to actually respond to that email. And they could just deploy code into production like day after day, and that's a very empowering thing. So we knew it was possible that when we started the company that we could achieve this, but doing it in practice for the past 2.5 years has been very, very, something we're very proud of, and something process we keep on trying to improve. So it really has changed. It can change the way that you think about your code, the scope of the thing that you're building, or how often you make changes or ship those changes to your apps, and that you can do it with confidence if you invest in the right pieces of infrastructure. That is 20 minutes on the dot. And so that's what I have prepared. Thank you. And there's a break right now, so if you guys have any questions, I'd be happy to answer them. Yeah, back there.
You talked about having 60+ services, and that y'all implement this in order to be able to scale first of the product as well as the people that come on.
Yes.
How easy or hard do you find it to take on new developers and learn all of these services?
So the question is, what's the process like onboarding a new engineer and them having to get familiar with all these services? Short answer is that they don't need to master all of those services. They need to understand what they do, particularly if the service that they're building or the thing that they're working on depends on that. But truly, it is truly independent. So as a real-world example, Kelly is an engineer of ours. I remember on day 3, she had spun up a service of her own, right? I mean, there's no way in Hades that she had mastered the entire scope of our infrastructure from A to Z, but she was able to create a service, and that is used in production today. So it actually helps quite a bit. You don't have to master all those, all existing 59 services, which was the number when she joined. Right. Great question. Yes?
Having 1 million services is one thing, but you have to do things with those services. So you have higher level services that use those services to make whatever higher level.
So the question is kind of like the hierarchy of services, and do other services depend on other services? Yes. That does happen. So, Dashboard, which is our website, uses the identity service, for instance. We have, everything is a service in our universe. So I think that it's about trying to find out whether or not a service should stand on its own. So we actually have had services that have grown to the point where we said, you know what? Now there is a segment, there is another service that could use a subset of this functionality here, and then we splintered that off, right? But it kind of has to meet a minimum criteria before, we're not microservices crazy, where we just try to take, if it's a unique operation for a particular service, you just keep it there within that service, right? Within an existing code base. You're not necessarily going to splinter off everything. So you have to, proceed with, with good planning, right? And reason as to why you'd want to have a separate service. Yes? What kind of data sizes are we transferring between the services? They're fairly small. I mean, we're talking these are all, very, very, fairly, I can't give you an exact number, but in the kilobytes, of HTTP requests with traditionally JSON data going back and forth. Yep. Yeah, the question is about authorization on the services, and that's something that I can't answer out loud. But yeah, I'd be happy to talk to you offline. Yeah, so the question was HTTP or HTTPS. That's another thing. That's a great question internally, whether it's not. I mean, again, I could walk off stage. We can go look at the code ourselves and take a peek. So yeah. Now, this is all internal traffic, right? So the requirements for HTTPS going in between our infrastructure probably wouldn't be required. But that being said, it really could be either. Mm-hmm. Any other questions? Great. Well, thanks for coming, everyone.